Good afternoon to all faculties. Welcome back for the last session of this FDP on research paper writing and IP rights. I am profusely elated to take this opportunity to introduce our keynote speaker, Dr. Shripad Garge sir. Sir is working as an associate professor at IIT Bombay. Shripad sir received his initial training in mathematics at Pune University before moving to the Harishchandra Research Institute at Prayag for his doctoral study. He was then invited to France and later to Germany as a visiting scientist. While he was in Paris, he secured his present job at IIT Bombay. He has visited numerous institutions in India and abroad for research collaborations. He leads a research group at IIT Bombay on algebraic groups, which comprises of PhD students, postdocs, and some talented undergraduate students. He is working on board of studies of several colleges in and around Bombay. Sir has also served on several committees of NCERT Delhi. He is winner of several awards, including an award for excellence in teaching at IIT Bombay. It's our immense pleasure to have such a wonderful personality with us to guide us. Over to you, sir.
Thank you very much. Actually, I am inside an examination hall at the moment, so I'll speak a bit with low volume for some time, and then my volume will increase. So can you all see the slides?
Yes, sir.
Okay, excellent. So yeah, I think, in India, we have this great tradition that anybody who does not know much about a subject feels that he is entitled to speak on the subject. So I am somebody who is still learning on how to do research, and maybe giving this talk could be seen as a way to learn how to do research. So actually, research is something which is related to questions. So the art of research is asking good questions. This is what we want to do. And then we would think about those questions and see what we can do with the questions. That is basically the idea. So when we think about question, quest is a part of the question. When we see the spelling for question, there is QUEST, a part of question, and one can say that question completes the quest. So quest is something which we are embarking on, and a good question will complete this quest. This is what we are going to do. So asking questions is something that can be traced back to a long way. Meaning one can say that Socrates is the one who started this method of asking questions. But it was there in our Upanishads also. Meaning our Upanishads all begin with the question Koham. That is the question that is there in the Upanishads. Koham is, saying, who am I? What is my goal on this earth? So why am I here? This is the basic question that everybody had, and that's how the whole philosophy came about. So Koham is the one which started, or you could also say that Socrates is the one who started asking questions. So in fact, there is a nice story about this, that Socrates once wanted to demonstrate to his disciple that, everything, the knowledge that needs to be given is already there in disciple. So all you have to do is ask good questions. Once you ask good questions, then it is already there. You can bring it out of the student. This is what Socrates believed in, and apparently there is a long story which I will not present here, but there is a long story where the Socrates asks questions and ultimately leads the student to coming up with the correct theory. But here is a fun thing, that to a question Socrates said, question everything. Meaning he wanted to say that question should be asked, and he said question everything, and the student says Why? So, even to that sentence, one can ask a question. But fun apart, of course, there is a merit in the Socratic way. And I should also tell you that all questions don't have easy answers. Meaning, if all questions had easy answers, then there would be no fun in working over, over some difficult questions. So, for instance, 1 second. 4 पर्यंत आहे. बुकिंग 4 पर्यंत आहे. माझं सुरू आहे लेक्चर. Sorry. Yeah. So not all questions have easy answers, and I'm going to ask some difficult questions to you now. So if I show you this photo and say, tell me which are the twins, then I don't think it would be an easy answer. Or if I say, which is the eldest person, somebody may say that this person here is somebody who is looking eldest, but then he is standing and this guy is sitting here. So which of those two is eldest? Another difficult question here would be, who is sleeping? So there are lots of difficult questions that one can ask, right? So this is just a way to, show that questions can indeed be very difficult to answer, but there are also questions which are interesting. So we will see a way to ask good questions. Of course, research is not something which can be written down in an algorithm. We can't say that if you do this, then your research will be complete. You will have a research paper out of this and so on. So I see that, this program has many nice lectures where you have had many excellent speakers coming and giving good talks on various things related to research paper writing. But doing research is not something that can come very easily to everybody. And this is why we need an advisor. So here we will look at an eightfold way of asking good questions. So this is Ratha Chakra from Konark, which has 8 spokes, and we will talk about eightfold way of asking good questions. This is the way which I learned from one very good mathematician by name Professor Ram Murthy. Ram Murthy is a professor of mathematics in Canada, and he is a very established mathematician. He is fellow of the Royal Society of Canada. There is a Royal Society in Cambridge in UK, United Kingdom, and there is a Royal Society in Canada also, which is also a very prestigious society. And Professor Ram Murthy is a fellow of that Royal Society of Canada. He is very senior age-wise, but he is still very active doing research, writing many good books, and giving excellent lectures. So he gave a lecture on this in IIT Bombay, and I really liked it. So I'm presenting it almost as he did, but with some of my own twists. So there are some changes which I'm going to make, and I will present a way to ask good questions. There are some 8 steps, and this is one way of asking good questions. Of course, many of you can come up with good questions in many other ways. I think now I can speak loudly. If there is anybody who cannot hear me properly, please let me know and I will speak even louder. Okay. So we start with the first step of asking questions is to take a survey. So once you decide that you want to work in an area, it may be some electrodynamics, it could be in some the virus study of viruses, I think, which is called virusology perhaps, or there is something called immunology in biology, or there could be number theory in mathematics, or you may study something in history. But whatever you want to work on, you should survey the existing knowledge. It should not happen that you are going to reinvent the wheel once again. You will spend a lot of efforts and reinvent the things which are already done. That should not happen. So the first step is that you should survey. And I will try to explain this with respect to an example. But so there are 2 parts. When we take survey, what does it mean? First of all, you will have to gather the facts. Correct? So whatever is known in your area, you have to gather the known information. And a very important step is to organize them. So these are the 2 things, that you have to gather all facts and you have to organize the known facts. And these two things can lead to a great understanding. Once you have your facts and you arrange them in some way, they lead to a very good understanding of the material. So, what is missing is also going to be revealed when you arrange your ideas properly. Okay, so for instance, how many of you know this mathematician? You may just raise your hand and say that you know this mathematician or you know this person. If I let me say that, let me not say that he is a mathematician, but how many of you recognize him? In fact, he is not a mathematician, he is a chemist. He is somebody who did chemistry. His name is Dmitry Mendeleev. So this is a Russian chemistry person, chemistry professor. And what he did was, yep, somebody raised a hand. Very good. So what he did was that he organized the existing knowledge of elements and he discovered a periodicity in their properties. So when he was writing, in fact, a textbook, he was writing a chemistry textbook, and so he thought that all that we know about these elements, there is the carbon, then there is nitrogen, there is oxygen, hydrogen, helium, and so on. So there are so many of them, and he decided to put them in some organized way. So put them in some order. He decided, okay, let me put them according to their atomic weight. And this is what he did. And what we came up with was the periodic table. So, initially he would have put it in a list. He would have listed all of them. And then he realized that there was some particular pattern. And so he used a 2 by 2 table. And so you start with hydrogen here. And then immediately you have at the end of the first line, you have helium. And then you start with the next row. So there are only 2 elements in the first row. Then there are, I think, 8 in the next row, and then some. And finally, the lower rows have longer, a more number of elements. And what is more interesting is that, in fact, he left some slots empty in his table because everything was not known when he organized his periodic table, when he came out with the periodic table. Everything was not known, and he predicted that there may be some elements which are not yet discovered. And he left some slots empty in those tables, in that table, and later they were filled. So, in fact, there are some Nobel Prizes which are given to proving the existence of some elements which corresponded to those slots. Of course, those are not very stable elements. We know that, when you go to higher atomic mass or higher atomic weight, the elements are not stable. They quickly decompose into something else. But the existence of these elements in a laboratory was proven later, and that was great work, which deservedly got the Nobel Prize. So, a very simple way to survey and organize the known knowledge has led to such great progress in chemistry. I don't think it would have been possible had he not, predicted that there are some such thing, had he not thought about putting them in a nice table according to their atomic weight. I don't know who else would have come up with the idea that, oh, there are some missing elements there. I think this is the only way, you write something. If you have a pack of playing cards and you know that some particular piece is missing, how would you come to know about it? When you either try to play with that and then you realize that, oh, this piece is missing, or what you will do is that you will organize them in some way. You will put all hearts in one place, all the clubs, all the diamonds, and all the spades. 13 cards in each pack, and then you suddenly realize that only heart has only 12 cards and there is no 13th card, and so you know that there is something missing. So organizing the known facts, that leads to great discovery. Since we are in the some of the earlier stages, I will give one more example. Now this is a mathematician by name David Hilbert. This is a German mathematician. So, Hilbert is, of course, credited for several things. In mathematics, there is a vector space, a structure on vector space, which is known as Hilbert space. So, Hilbert has name to meaning. In mathematics, there are various theorems which are credited to Hilbert. There is something which is called Hilbert 90 theorem. There is some reason for the number 90 coming there. Then there is the Hilbert 60 theorem also, and several other theorems. But what he was also known for is that he organized 23 problems at the ICM in 1900. So let me tell you what is an ICM. ICM stands for International Congress of Mathematicians. All mathematicians throughout the world come together once every 4 years. Once every 4 years, they come together and they discuss the recently developed mathematical theorems, mathematical results, and people who have done excellent work are invited to give lectures at this ICM. And there are some very prestigious prizes which are given in the ICM. So those are called Fields Medals. They are supposed to be equivalent to Nobel Prize, in the sense that there is no other prize in mathematics which is above Fields Medal. Okay, so typically one, two, or four people, or sometimes three mathematicians are given these prizes, and some very excellent mathematicians come and give lectures. So Hilbert was asked to list 23 of his of some 23 problems which will shape the mathematics in the coming century. Hilbert was know this that Hilbert was only 38 years old that time, but he was already known to be one of the greatest mathematicians who was known to be polymath. Polymath is somebody who is well versed with multiple areas of mathematics. So Hilbert was well versed with multiple areas of mathematics that time, and it was thought by consensus that if there is anybody who can give a direction to mathematical research in the 20th century, it would be Hilbert. So the organizers of this ICM, I think it was in France somewhere. So the organizers requested him to give a lecture explaining only some list of problems which would, according to him, be important in the coming century. And much of the mathematical research in the following century was motivated by these problems. In fact, some of them are not solved even now, and those are supposed to be very difficult problems. So if I could just tell you, I won't list all 23 problems here, but there are some new areas which came up with his work. So there is this thing called transcendental number theory. So transcendental number theory is the study of numbers which are very difficult to study. So for instance, if you look at the integers 1, 2, 3, 4, or their negatives, -1, -2, -3, -4, and so on, and together with 0, you have what is called the set of integers. So integers are then contained in rational numbers, which are like p by q, where q is non-zero and p is any integer. So it can be like 3 by 5 or 7 by 20, 24. These are the numbers which are called rational numbers. Now you may know that when you draw a line, you call 1.0 and you call some unit as 1. Okay, so we have a line, we fix a point, call that point 0, and you choose some distance, and then that distance from 0, you call that 1. Once you have this, then same distance ahead, you can put the number 2, same distance ahead, you can put the number 3, and so on. On the negative side, you will have -1, -2, -3. Okay. Once you have this, you can also write down the rational numbers in this. The distance between 0 and 1, you divide it by 2 and you have 1 by 2. Or you divide it by 3 and you have 1 by 3. There are some nice triangles which you can use to compute these distances using the similarity of triangles, right? So the rational numbers can be plotted on the real line. But here is a fact, very elementary fact, that there are some numbers on the real line which are not rational. So for instance, √2 is a number. It's a real number whose square is 2, but this number cannot be written as p by q. And there is a very beautiful proof of why this cannot be written. I will not do it here, but you can search on the internet, you ask for square root of 2 rational number. If you just say this, then the proof will come. So these square root of 2, square root of 3, square root of 100, that is 10, so square root of 101. So these are the numbers which are bigger than rationals. Okay. But yet, square root of 2 is an easy number because it satisfies x square equal to 2. So there is a polynomial x square minus 2. And to write the polynomial, you are using only integers. The coefficient of x square is 1. The constant term is -2. Okay, so you have a polynomial over integers and you have a real number which satisfies that. Square root 2, when you put in the polynomial, you are going to get square root 2 square minus 2 and you get the value to be 0. So square root 2 is a solution to x square minus 2. These numbers are called algebraic, and it's a beautiful fact that there are lots of numbers beyond these in the real numbers, and they are called transcendental. You know, when you do some adhyatma or you do some philosophical, high study of philosophical ways, you say that, you know, we are studying the transcendental thing. Transcendental is something which you can perhaps see, but you can never reach there, at least in one lifetime. This is what we think about transcendental things. So transcendental number theory is something which is very difficult to track. And the seventh problem that Hilbert had suggested, its solution and all the attempts which were made to solve this seventh problem led to research in this area called transcendental number theory. The eighth problem is the Riemann hypothesis. I will come perhaps later again with the Riemann hypothesis, and I will say what is Riemann hypothesis later when we come to that. Ninth problem relate to what is called development in reciprocity laws. In fact, there are many books, this thick books, at least 10 of them I know, which are written on various of these reciprocity laws. So, you know, the mathematics is nice in that sense. You know, there are some laws you can write down, and the mathematical objects, which can be numbers, they can be sets or something else, they satisfy these laws. So the ninth problem led to what is called development in these reciprocity laws. There is also one problem which studied basic thing about mathematical logic. So what are the sets which can be written down axiomatically? So this problem is actually also connected with the theoretical computer science. Yeah, is there any comment? So I don't know how we are taking the comment. Maybe we can just take them at the end. If you have anything else, please note the thing you have, and then we will discuss those things in the end. Okay, so this 10th problem, it motivated new studies in mathematical logic, and these days a lot of research is being done on this, even in computer science, what is called TCF, theoretical computer science. There is this arithmetic theory of quadratic forms, which was developed using the 11th problem. So there are multiple problems which led to new areas, and these days these are themselves areas of mathematics. They are not part of number theory or algebra or algebraic geometry or so. These are themselves some new areas of mathematics. So this is all that we have. Remember, the first step for us is the survey method. Okay. Next, second step is called observations. So we have gathered our facts, we have put them in some way, we have organized them, and now we are going to observe the things and see what comes out of the observations. The observations have to be done very carefully. Once you do careful observations, they will lead to patterns, and patterns lead to questions. So I gave example of Mendelev's table, where Mendeleev observed that there are patterns, but there are gaps. And so he had a question. He posed this question to see whether these gaps can be filled, whether you can discover these elements which will have those corresponding properties. So patterns will lead to questions. There is this Michelson-Morley experiment, which showed that there was no need to postulate a medium for the transmission of light. You know, meaning when I was in school, I think there was something called as ether, because people thought that if light has to go, then there has to be some medium for that. We are getting the sunlight. When the sunlight enters our atmosphere, the atmosphere of the earth, then of course, you know, we have air and there is a medium for the light to come through. So people had this question as to what was there outside the atmosphere of the earth, and they postulated that there must be something which they called ether. So they said vacuum is made of ether. They defined ether to be something which makes up vacuum. But this is the experiment which showed that there is no need to postulate a medium for the transmission of light. Meaning, this is an experiment which, you know, there is this question and people perhaps still don't understand whether light is a wave or whether it is a particle, whether there is this thing called photon. And of course, now with string theory, then people are saying that these are not particles, these are not waves, but these are actually strings. And depending on whatever mood the string takes, it can act like a wave, it can act like a particle, or so on. That's the latest research, perhaps. But this is an experiment which said that you don't have to have a medium. The light can travel even if there is no medium. This is what this experiment said. And of course, who can forget the Eureka moment of Archimedes? So people who don't know the story, I can maybe quickly repeat this story. So Archimedes is a Greek mathematician. He was a mathematician. And there was this king of Greece, and he had his daughter. The daughter was very gravely ill. So he made an announcement throughout his kingdom saying that, whoever comes and cures my daughter, whoever comes and makes my daughter better, I will give him gold weighing in weight equal to that of an elephant. So I will give the doctor or whoever comes, I will give him gold. And how much gold? The amount of gold is equal to the weight of an elephant. He just, announced this, and there were people who came, and luckily, one of them succeeded. The daughter was cured. And then there was another problem. Now, how do you measure the weight of an elephant? You can't have a tarazu, where you can put an elephant in one side and then keep on putting some gold nuggets and see when the weight actually becomes equal. That's not possible on the, meaning elephant will not sit still. That is of course, the list of the problems. There are many difficult problems in weighing the elephant. So how do you do it? And so he posed this question to Archimedes, who was in his darbar that time. Maybe this is the version of Birbal for Akbar. Akbar would, without thinking, announce something, and then it would be the responsibility of Birbal to complete that. So he said to Archimedes that, you tell us, how do we do this? And Archimedes was stumped. He did not know how to do. So apparently, those days people would not take bath every day. And so Archimedes thought that I need to have a quiet moment. Let me go and take a bath. This is what he thought. So he went to his bath house. There was this nice tub. We see a tub here with Eureka written on that. He didn't have this tub. He had his separate tub. So he went to his tub, and when he lied down, he observed that the water was completely full to the brim of the tub. And when he lied in it, he realized that some amount of water was, of course, something spilled over. The water was completely to the brim of the tub. It was full. And when he went into it, some amount of water, of course, has to be displaced. And then he had this Eureka moment. He said, yes, this is what it is. So he said that if I put, not myself, but if I put a bag of gold weighing equally as much as me, then the same amount of water would be displaced. And this was his idea. So what he did then later was that he improved on this idea. He had a boat. He said, let's have a boat, which is an empty boat, which is in the sea. And once the sea is quiet or whatever, meaning you measure how far the mean sea level or something, you mark the level of the sea that is there on the ship. Then you put the elephant on it. So the boat will go down a bit because of the weight of the elephant. You make that mark. Take the elephant out. The boat has again come up to the previous mark. Now keep on putting gold in it until it goes to that mark of the elephant. That's it. That would tell you how much. He didn't tell you what was the weight of the elephant. He didn't say that the elephant was 300 kilos or something. He said, I'm not bothered about the weight of the elephant. I want to know, can I measure gold in weight equal to the weight of an elephant? And that is what he did. So this was the observation which led Archimedes to come up with this Eureka moment. Eureka is, in Marathi we say, sapadla, sapadla, mil gaya. It's that kind of, that is the meaning of the word. But now the meaning has changed. Whenever there is a discovery, a great discovery, people say Eureka, Eureka. This is the legend of Archimedes. So this is what is done with observations. Of course, there are some funny things also. when someone is excavating in the desert and you suddenly come across a conical object, then the natural thing could be that one of them saying to the other that this could be the discovery of the century, depending, of course, on how far down it goes. So your observation will also lead to something interesting. Of course, it should be a observation of something which is very deep. That is the object. That's the message we can take from here. So we had survey as a step 1 and observation as step 2. Next is what is called a conjecture. I think this conjecture, although this is perhaps known, this word is used in many areas, but it's used mainly in mathematics. So what do people do in mathematics? They observe a few things, and then these observations lead to what are called conjectures. And well posed is just an adjective. It doesn't really have a meaning. But conjecture is a statement which you believe to be true. And perhaps you are not able to prove that right now, or you have enough things at your hand and you don't have time to work on it, but you believe that this should be true. And so whenever, meaning sometimes there are research papers in mathematics which talk about conjectures. So people who study some objects, they will make list of some properties, they will write down some observations, and then they will say that from these observations, we believe that this holds, but we do not have a proof. And then that is the statement which is called a conjecture. So a conjecture, in fact, can do both things. It can inspire progress in an old discipline, or it may even inspire a whole new discipline. One of the very well-known conjectures is what is called Fermat's last theorem. So there was a mathematician by name Pierre de Fermat. I think so Fermat's last theorem. So this is called Fermat's last theorem because it was not the last theorem that he wrote or proved. It's not that he wrote that and then that's it. He stopped doing mathematics. That was not the thing. Fermat came from France, and I think he was in 17th century or 18th century, and there is this long battle between French mathematicians and British mathematicians. So people from France would say that we have proved this statement, and they would only send the statement to Britain, and British people would send their own statements, and then they will say that, okay, let's see if you can also prove this. So those were the things, and Fermat had lots of such results. Of course, he had proofs of them, but sometimes he would only write down the statements and send them by letters to other mathematicians. And later, 100 years later, 150 years later, all the statements that Fermat had written were proved. Maybe one or two were disproved, but most of them were proved. And this is the only thing which remained. So Fermat's last theorem said that if you look at the equation x power n plus y power n equal to z power n, that has no solution. In integers, if you put n to be bigger than or equal to 3. For x square plus y square equal to z square, we know there are several squares which sum to give a square. For instance, 9 plus 16 is 25. If you draw Pythagorean, if you draw a right angle triangle with 3 and 4 as the edges which are making the right angle, then the hypotenuse square is equal to square of the sum of the squares of the two sides. So if you draw a right angle with length 3 and length 4, the hypotenuse will have length 5, because 3 square, which is 9, plus 4 square, which is 16, give you 25, which is 5 square. So there are solutions for x square plus y square equal to z square. In fact, there are infinitely many solutions, and you can write them down easily. There is a formula, etc., etc. So all this can be done, but beyond 2, there are no solutions. Of course, you can put 1 power n plus 0 power n equal to 1 power n, but those are what are called trivial solutions. So there are no solutions which have no 0. If you put 0, then a power n plus 0 power n is a power n. Those are not the solutions we are looking at. So there are no non-trivial solutions. That was what Fermat said. He claimed that he had a proof, but the proof was nowhere to be found. So he said it is his theorem, therefore it was one of the Fermat's theorems, but it was the last one which was not proved. And so this was called Fermat's last theorem. And this was proved ultimately by, again, as fate would have it, two British mathematicians, but they were not in Britain that time, they were in the United States, they were in the University of Princeton. So they are Andrew Wiles and Richard Taylor. These are the two British mathematicians who finally proved this theorem. But this was done, the proof was in 1997, just 25 or 26 years back. Okay, it is a recent thing to what we are talking about. So we are talking about Hilbert, we are talking about Archimedes even. So compared to that, this is a recent development, and Fermat is from 17th or 18th century. So it took a long time, and it required development of this whole new theory called algebraic number theory, studying numbers with help of algebraic methods, what are called groups, rings, etc. Is there some comment from anyone? Some mic is on. Yeah, thank you. Okay, so we were talking about conjectures. Our own mathematician Ramanujan also made several interesting conjectures. In fact, there was Ramanujan centenary recently, and the centenary had, meaning you will know that Ramanujan passed away when he was 32, not even 50 years old. So there was a conference when making 50 years of Ramanujan's birth. Okay, and in that conference, it was held in UK somewhere, I think, in the England. And in that conference, several people talked about Ramanujan's work. And there were some talks devoted to some conjectures which Ramanujan had made. And his mentor, Professor Hardy, was there. There were several other mathematicians. And I should tell you that Hardy himself made this comment. He said that if we are thinking about who is a complete mathematician, suppose we give 100 marks to a complete mathematician, then I, meaning Hardy said of himself that I would get only 50 marks. My colleague Littlewood would get only 70 marks. But Ramanujan would get 100 marks. This is what he had said. So Ramanujan is the one who made lots of calculations. He had a slate. If you have seen this movie about Ramanujan, I think it's called A Man Who Knew Infinity. That's the movie on Ramanujan, or there is another earlier version. There are two movies made on Ramanujan. So there you see that Ramanujan was writing on his slate, furiously writing, furiously doing calculations. He was getting new ideas every day, and he did not want to waste time. He worked hard, he overworked, and that was what actually led to his death, unfortunately. But he was getting these ideas and just he could not stop, and he just had to work. So I will tell you what kind of calculation he did. This is, he defined a function called tau function. So here we see an equality. On the right hand side of that equality, there is an expression which is an infinite product. This pi like thing that you have, below which I have written n bigger than 0, that calls for product. So you have q, and to q you are multiplying 1 minus q power n whole thing raised to 24. Now why 24? That can be answered if you do first year PhD course. You will know why 24 is important. Okay, so you could not have, meaning this does not make sense for something smaller than 24. It makes sense for larger number, larger than 24, but then those are even difficult to work on. Okay, so Ramanujan said that you look at this q into 1 minus q power n whole thing to the power 24 and take product over n going to infinity. So you will have 1 minus q, you will put n equal to 1, and you have 1 minus q power 24. You can use binomial expansion and write down that product. It will have terms for 1, it will have terms for q, it will have terms for q square, etc. and so on. Then the next term will be 1 minus q square into 24. You can write that further. But observe that when you have the third term, you had the first term which is q, which is right here outside. Then you had the next term which was 1 minus q power 24. After that, you had 1 minus q square power 24. This 1 minus q square power 24 will not have anything contributing to q, because it starts with q square. So it is like, if you're writing 1 plus q square square, that would be 1 plus 2 times q square plus q power 4. The terms which will come will be some powers of the terms which are already there. So if you have 1 and if you have q square, there is no way you can write q in terms of 1 and q square. You are only allowed to take products. So we know what is going to be the formula for q. We know what is going to be the value for q. You don't have to go to q square for that. So the value for q will be equal to tau n. That is known as the value of tau at n equal to 1. Similarly, if you are looking at n equal to 2 on the left hand side, then you would look at right hand side, you will look at q, 1 minus q power 24. That will give you something with q square. And then you have 1 minus q square times 24, which will also give you something for q square. After that, it will be q cube and onwards. So q square will not come from them. So tau 2, which is the coefficient of q square, can be also computed. So in fact, Ramanujan sat down and computed several hundreds of terms of this. And he realized that the first coefficient is of course 1, because you have q common here, multiplying to everything. So you will get 1 from each of the products, which will give rise to q. Then there is a q square which comes with minus 24 as the coefficient, which is coming because of the binomial expansion here. 1 minus q to the power minus 24 will have the second term equal to minus q square. So that minus q, but then there is a minus, there is a q sitting outside. So this q and that q will give you q square. Okay, so you had minus 24 q square. You can compute q cube also, because you know what is 1 minus q square. Their powers raised to 24, and then you have the q sitting outside. So that gives you coefficient of 252 for q cube, 4th power, 5th power, and so on. And in that, Ramanujan observed that when you take the power for 2 and the power for 3, take the product, you will get the product coefficient for 6. So minus 24, which is the coefficient of q square, and 252. If you took the product, you will get the coefficient for q power 6. If you took the power of q square, which is minus 24, and q power 5, which is 4830, you will, taking product, you will get the coefficient for q to the power 10. This worked, not always, but exactly when these coefficients, so m and n, they were co-prime. That means there was no common factor. 2 and 3 have no common factor. There is no single integer which divides both 2 and 3. Similarly, 2 and 5 have no common factor. There is no integer which divides both 2 and 5. These are what are called co-prime numbers. So Ramanujan conjectured that whenever you take m and n to be co-prime, it can be 4 and 5. 4 has factors 1, 2, and 4. 5 has factors 1 and 5. There is no common factor other than 1. So you take those coefficients, take the product, that should give you the coefficient for q power 20. He computed many such coefficients and he observed this pattern. And then he made this conjecture that tau of m into tau of n is tau mn whenever they are co-prime. Now, when they are not co-prime, you can think about squares. I will write q4 as 2 square. So I can write 4 as 2 into 2, but 2 and 2 are not co-prime. There is something which is there. The divisor is 2. Or if you have 2 and 4, they are not co-prime because 2 divides them both. But any integer can be written down as product of prime powers. And if you knew the value for prime powers, you can use the first step to compute the value at your integer. So if you knew what is the value for 4, if you knew what is the value for 5, you will know the value for 20. To know the value for 5, you have to compute value for 5. To know the value for 4, you have to compute value for 4. Value for 2 is not sufficient to give the value for 4. But the value for 8 will require the knowledge of only the value for 2 and value for 4. Or if you want to go to 16, it will require the knowledge of q power 4, q power 8. This is what is called the second order recurrence relation. That means you want to know the value for p power r. You need to know what are the values for p power r minus 1 and p power r minus 2. That's it. Two previous stages. That's why it's called second order recurrence relation. You should know what are the previous two powers, their values. Then you can compute the value for p power r. So once you know the value for p and the value for p square, you can use this conjectured recurrence relation to compute p cube. Now you know the p square value, p cube value, so you can compute p power 4. Now you know p cube value, p power 4 value, you can compute p power 5. All these prime power values can be computed. Once you have the values for prime powers, you can put distinct prime powers together and compute value for all n. What a beautiful observation of Ramanujan. And he further concluded that you also have that mod of tau p is less than p power 11 by 2. Remember, this 11 is 1 less than 24 by 2. So the relation between this power and 24 is that this you multiply by this power by 2 and you subtract 2 from this number and you get the same thing. So meaning 24 minus 1, 24 by 2 minus 1 is twice of the power of p. These were the three conjectures which Ramanujan made in 1916, and they were proved much later by this Belgian mathematician by name Pierre Deligne. This was proved in 1974, almost 60 years. And Pierre Deligne got Fields Medal for this work. So this work was considered as great as a work in physics would be called considered great if it deserves a Nobel Prize. So this was one conjecture made by Ramanujan. There are several other very interesting conjectures made by Ramanujan, which people are still working with, and it's leading to some very, very great development in mathematics. So we had three things. We had survey, observation, and conjectures. Now we come to the fourth step, which is called reinterpretation. Sometimes whatever knowledge you have, you may observe, you may collect it in a nice way, but it also depends on how you interpret it. So what it means is that, you know, whatever is known to you, you should try to see it from a different point of view. This is what is called a reinterpretation. So for instance, if you look at gravity, what was gravity? The idea about gravity kept developing. Initially, Newton said that it's a force because, you know, Newton observed that the apple fell from the top and it hit him on the head. And so maybe some Bindu was awakened and suddenly he had the idea that, yes, this is gravity. And he believed that there is something which is forcing the apple to fall down. Whenever the apple is not hanging by something tied up, if it is left as it is, stationary, it will fall down. So it's a force. This is what he said. But Einstein said, no, it's not a force. It's a curvature in space. So let me try to, first of all, you know, there is this statue of Newton. There is an institute in Pune, which is called IUCAA. IUCAA. So it's called Institute, it's called Inter-University Center for Astronomy and Astrophysics. IUCAA. Inter-University Center for Astronomy and Astrophysics. It's a very well-known institute in Pune. It's in the university campus, Pune University campus. And very beautiful institute. Professor Narvikar, Jayanta Narvikar, he was the one who developed this institute. So there are many statues. There is a statue of Aryabhatta, I think. There is a statue of Bhaskaracharya, and there is a statue of Newton. And if you see below Newton's statue, near his right foot, there is some spherical object that is supposed to be an apple. And so Newton is actually looking at that. And when we visited Ayuka, I was a student at Pune University. I think Madam just now, while giving my introduction, she said that I did my masters from Pune University. So I am a student of Pune University, and I used to visit Ayuka once in a while. So when we went there, we used to joke that what is Newton thinking about? Is he thinking why this apple fell from above, or how come there is an apple while the tree next to him is not an apple tree, it's a banyan tree. You can see that this is the banyan tree. हे वडाचं झाड आहे ज्याच्या खाली न्यूटनचा पुतळा आहे. So Newton may be thinking as to the force of gravity, or he may also be thinking why apple has come from the banyan tree. Okay, so this was what Newton said, that it's a force, whereas Einstein said no, it's not a force, it's a curvature in space. What is a curvature in space? So if you have this, we have Earth, and there are objects in the space which are coming towards Earth. But when they are coming towards Earth, they also experience the gravitational pull from other objects. And so they don't come and bang on the surface of the Earth like that. They curve their direction. Their path gets curved. And so this picture that you have below the Earth, this is a hypothetical picture. This is supposed to tell how the objects will pass through. This is what Einstein said. That Einstein said it's a curvature in space. So the space is curved. You don't look at the space as it is. The space is not just, meaning if I look at, I'm in a big, huge classroom sitting right now. So you can perhaps see some board behind me. Yeah, so there is this board. So I'm sitting here. There are these empty benches because right now the exam is done. And I see the space around here, but the space, actually, I don't see the space. I only see the walls and other objects, but the space has a structure of its own. This is what Einstein said, and he said, in fact, that the space was curved. That's a reinterpretation. I think now there is, gravity, it goes beyond all of these. There are what are called gravitons. They are what are called massless protons, or maybe no, not protons. Fundamental. These are called fundamental particles. So we at the time of Mendeleev, we had elements. Then people broke the elements down. So you had atom, and you had electrons. Then atom had neutrons and protons. And then there are some even fundamental particles. And maybe 100 years later, there will be some particles which will make up these fundamental particles. Even that can happen. Who knows? So the existing knowledge can always be reinterpreted in many ways. There is this unique factorization theorem in number theory, which says that you take any number, you may take 20, and 20 can be written as 2 into 4 into 5. 2 power 2 into 5. So you have 4 into 5, which is 2 square into 5. And there is a uniqueness, which says that the number of primes which divide 20 are 2. 2 divides it, 5 divides it, 2 divides with power 2, 5 divides with power 1. So you have 20 equal to 2 square into 5. There is no other way to write 20 as product of primes. You may permute. You may write 2 into 5 into 2, or you will write 5 into 2 into 2. But other than the permutation, there is no other way. This is what is called a unique factorization theorem. Euler actually reinterpreted this theorem, and he defined this function. So he said, you look at 1 power s, you take s to be any complex number. And if you are worried about what it means to say 2 power a complex number, don't worry. That definition is not required for understanding this. All we require is that whenever you have n power s, you can use this and write it as p1 power a1 to the power s, p2 to the power a2 to the power s, plus dot 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 pk power ak to the power s. So the nth term is actually product of the various power terms, just like we had for Ramanujan tau functions. Here, these are the numbers themselves. Okay. So this was the function which Euler defined, and Riemann studied this function later, and that is what led to his Riemann hypothesis. So Riemann was before Hilbert. because I told you that Hilbert talked about Riemann hypothesis as one of his problems, and Riemann hypothesis says that a function zeta s has 0 when s is equal to 1 by 2. When the real part, s is a complex number, so it will be some real part plus I times a complex some another real part. Whenever the real part is 1 by 2, the function value will be 0, and when the function value is 0, the real part has to be 1 by 2. This is what is called Riemann hypothesis, and that is not yet completely solved. Um, when I was thinking about this lecture, I was reminded of one more story from our, what people call mythology, but what I like to call it as history. So this story says that when the Dev, the Danav, and the Manav, so gods, demons, and human beings, when they were residing on Earth, they decided that it would be good if we all live together harmoniously. We don't fight with each other and so on. And let's go to Prajapita Brahmadev. Brahmadev is the one who would take care of them all. So they decided that let's go to Brahmadev and ask for knowledge. And let's make ourselves knowledgeable. This is what they decided. So they went to Brahmadev, and then they said that we have come to you with this quest. We have come to you with this question that we want to know what is the ultimate knowledge. Brahmadev was very happy because he was seeing them fighting all the time. The Rakshasas will give trouble to Manavs, and then Manav will pray to the Dev, and then Dev will come and bash the Danav and so on. So all fighting happening all the time. So he said, very good. It's really nice that you have come to me, but before you gain this knowledge, you have to purify yourself. So what you do is that you sit still, you make tapasya for 1 whole year. You meditate for 1 whole year, and at the end of 1 year, I'll come and give you the ultimate knowledge. So all this said, okay, fine. So they went and sat and started meditating. While they were meditating, Brahmadev realized that all these 3 types of, the Brahmadeva's praja were getting rid of their impurities. So the Devgan was getting rid of the bhog. Devgan was always, they had all the powers. So they were always enjoying the pleasures of the secular things. They would, listen to music, not do any great work. They would, have this surapan and so on. So they were always enjoying the materialistic pleasures. While meditating, they realized that this is not the thing that will lead us to anything which is good. The Danavas were always thinking about violence, always thinking about going and bashing up somebody else, or if there is nobody else to bash up, let's fight among ourselves. This was what Danavas kept thinking about all the time. And so when they were meditating, they realized that this is not what will take us to higher level. And the human beings also realized that they were too much attached to whatever small things that they had achieved, the prapanchik things, what we say. They were attached to those, and they realized that we have to get rid of these to achieve higher level. So after 1 year, Brahmadev appeared in front of them and was very happy and said that I have already seen that you are getting purified, and so I'm ready to give you the ultimate knowledge. This is what Brahmadev said, and so they were all listening. So Brahmadev thought for a while and then uttered only one word, or we can even say only one letter. He said, the, and then he remained quiet. But because of the tapasya that these all 3 types had done, they could reinterpret the in the correct way for them. So the Devas then said that, yes, Pita Brahmadev, aapne jo bola hai, whatever you have said, we understood its meaning. For us, it means daman. We have our indriyas, we have our 6 senses. They were getting over us. They were becoming dominant over us. We have to daman them. We have to learn to control our own senses. and then we will reach the higher senses. So they did the pranipat and they went away. The Rakshasas came forward and then they said, we understand the meaning of the. For us, it means daya, that we should not go and trouble the lesser people or the human beings or the weak persons. We should not do that. We should not think of hinsa, we should not think of violence, but we should think of daya. And they also did pranam and went away. And then the Manavas came forward and said, then they said, we were too much attached to whatever we had achieved. We understand that the means dan for us, meaning whatever we have, we should share it with others. So the is a single word, it's a single letter, but it was to be reinterpreted by all of these three species, the Devas, the Danavas, and the Manavas, and so it led them to higher levels. But it required some tapasya. So our previous stages, the survey, the observation, and the conjectures, if you do them properly, you will be able to reinterpret the existing knowledge. We go to the next level. I think I have already spoken for 1 hour. I will maybe now there are not too many such slides. We remember we talked about eightfold way. So there are 4 steps still remaining, but let's see what they are. This is called analogy. So when there are 2 theories which are going side by side, they are analogous. Whatever is happening in the initial stages of this theory, the second theory may come later. But the initial development may be too much similar to whatever is happening here. Then it's very natural to see if the similarity will continue. Right? These are very natural things that one can think about. Okay. This is what is called analogy. You have some things in one theory, you have some ideas in one theory, and you want to see whether those ideas work in the other theory. And this is what I alluded to also. You had 1 upon n power s. Remember, we had whenever, in fact, 1 upon n power s has the property that if you take 1 upon 2 power s into 1 upon 2 power s, you get 1 upon 4 power s. The square, the product of 2 terms will give you the next term. The product of 2 and product of the 4th term will give you the product of 8th term. But what is also true is that the co-prime things also work. Meaning you have 2 second term and third term, the product will be the 6th term. And that is what you are getting here. Remember, our Ramanujan conjecture was especially that the values of tau n behave like when you know the value for p and p square, you can compute all the p power values. And once you know all the p power values, you can compute all the integer values. This is what Ramanujan had. So there are some properties of this first series, 1 upon n power s, which are followed by the second series. The first series can be written down in this way. This is what is the reinterpretation of the unique factorization for integers. Can we write the second series also in the similar way? That was the question and that was answered. And this is another good work which was done by a mathematician, a German mathematician by name Hecke. So these are what are called the Hecke operators, and the Hecke operators correspond to these numbers which appear in the denominator of the product terms. So this is the analogy which signaled a new beginning in the theory of what are called L functions and representation theory. So I talked about Hecke. This is that mathematician from Germany, Heinrich Hecke. So H. Hecke. The next mathematician is of Indian origin by name Harishchandra. If you go outside in the world of mathematics and you ask who is the well-known Indian mathematician, the answer is Ramanujan. There is nobody else, no other as famous mathematician from India. But if you ask who is the second well-known mathematician, and the answer is Harishchandra. In United States of America, there is an institute called Institute for Advanced Studies. One very wealthy person, he decided that he would donate huge amount of money so that people can work on new things. And he consulted several scientists in different areas. And then he decided that he will build an institute for mathematicians. Because in mathematicians, there was unanimity as to who are the best mathematicians. All the mathematicians knew these guys, they are the best. This was unanimous view. In physics, there was no unanimous view. Some people said these four are the best. Some other people said no, these four are the best, and so on. So there was no unanimous view. But in mathematics, there was unanimity. And so he started this institute with mathematicians as the what are called permanent members. So these people can stay there. There is no teaching duty. They have to only do their research. There is no work at all. You can be your home, you do your research, you keep publishing your research papers, and maybe there will be a seminar once every year where you present your work. Nobody will make comment of how good or how bad your work is. It's for you to decide. You know, when you have to decide how good or bad your work is, that's a very big responsibility. When you know that somebody else is going to decide how good my work is, you can work with that. Because if that person says this is not good, you will say, he doesn't understand my work, or he is not happy that I have put this, and so on. But if you have to make comments about your own work, you will come and present your work. And then it's up to you to decide whether it is good or not. Nobody else will make a comment. That is the thing which, you will not be able to sleep if you have not done good work. And that's the thing which keeps a person doing good work again and again and again. So Harishchandra was a person who was one of the first permanent members at this Institute for Advanced Studies. Here is the person called Robert Langlands. He is also later, he also became a permanent member at the Institute for Advanced Studies, but not when Harishchandra was there. He was a student of Harishchandra in some sense. So these people worked on the theory that Hecke had developed, what is called L functions. Harishchandra developed it, and then Langlands took it to another level. The analogy worked very well for these mathematicians. So survey, observations, conjectures, reinterpretation, and analogy. Now this is what is called transfer, meaning the point here is that you have to transfer the idea in one area to another. This is not like analogy. Analogy is where you had similar structure in both of them, and so you go one step further in first theory and you try to see if the same method works in the second theory. But here you are transferring the idea from one area to another, and there may not be any analogy, a very simple analogy to look at it, but you had some idea here, and you will try to see whether the idea works in the other thing. So number theory is something that we have spoken a lot, and you write any number as product of primes. So you want to decompose, keep decomposing things until you cannot decompose further. You want to do it in that way. And this is what we do when we study modules, or when you study what is called a group. Or even otherwise, if you have an object, this is something that we learn in physics in school, that everything that we see is made up of small atoms. It's made up of atoms. This is the idea which came up from the number theory, that you can write down every number as product of primes. Primes are something which cannot be further divided. Atoms, those days, were something which cannot be further divided. In fact, there was a Rishi, there was a scientist from India, from Gujarat, by name Kanad. He is the one who propagated the idea of Kan, and he wrote it down explicitly. Meaning, people say that Indians would do great work, but they would not write it down and so on. But Kanad wrote it down very precisely. He said that Kan is that part of the object you have which cannot be broken down further, and if you break it down, the properties of the object will be lost. So if you have a molecule of oxygen which is made up of oxygen atom, if you break this atom down and you break it up into electrons, protons, and so on, you don't have oxygen anymore. The properties of the object are no more there when you break it down further. He did not say that you cannot break the atom down. He did not say that. He agreed to the possibility that atom can further be broken down. But if you break it down, the property of the object will not be there. If you have a sugar molecule, if you have water molecule, which is H2O, H2O is the smallest thing in the water. So it is the kana of the gel. If you break it down further, you don't have Jala Tattva there. You will have hydrogen, you will have oxygen, but there is no water in that. If you write it as H2O, that is the smallest unit of water that you have. This was the idea of Kanad. So this is what is the transfer idea. And sometimes you don't even get uniqueness. Yeah, meaning here we have these modules which you want to write it as something as sum of irreducible modules, but there may be multiple ways to write it. And so you don't have uniqueness. Even then, the idea is that you write an object in terms of simpler objects. Seventh is induction. I think this induction is the thing that many people will be familiar with. So let me start with an example. What we want to do is that we want to generalize. Somebody can observe that when you take 1 cube plus 2 cube, 1 cube is 1 and 2 cube is 8. You sum them and you get 9, which is the square of 3. Okay, so 1 cube plus 2 cube is 3 square. If you take 1 cube, 2 cube and 3 cube, so 1 cube is 1, 2 cube is 8, so that gives you 9. To that, you add 27. So 27 plus 9 is now 36, which became the square of 6. If you now want to add 4 cube, what is 4 cube? 4 into 4, which is 16. 16 into 4 is 64. You add 64 to 36, and what you get is 100, which is the square of 10. So indeed, it seems there are these 3 dots which say that the things go on, the pattern continues. And you can wonder what will be 1 cube plus 2 cube plus dot 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 plus n cube. If I was giving this lecture on the board, or if I was teaching this to an IIT class, I would ask students to come up with the answer. Is it going to be a square on the right hand side? And if it is a square, what square will it be? It will be square of what number? So you can actually prove that this is going to be the square of n into n plus 1 by 2 whole square. N and n plus 1. Now n may be odd, but then n plus 1 will be even, or n may be even already. So the product n into n plus 1 will be an even number. That means the n plus 1 by 2 will be an integer. And so it's a square of an integer. This is what we get. This is something which can be proved by what is called the method of induction. That you assume that the result is true for n minus 1. You will get a suitable such number square there. You add n cube and write down the formula and find out that it is the square of n plus 1 by 2. So you are generalizing whatever was existing. This is not simply the transfer. You are making it bigger. You are generalizing it to suit the new place where you are putting the idea. So for instance, we have the Riemann zeta function and the Ramanujan zeta function, right? Meaning you had this 1 upon n power s, and then we had the tau n upon n power s. So these were already obtained by using some analogy or transfer of the ideas, etc. But in fact, these are themselves particular cases of something which is very big. The Riemann zeta function corresponds to what is called the group GL1, and Ramanujan zeta function corresponds to something what is called GL2. So there is GL3, there is GL4, there is GL100, GL2024, and so on. There is a huge generalization out there, and there are huge, this is what is called Langland's program. This whole theory is not called theory, it's called a program, because it's a way in which many mathematicians can come together and explore what is happening throughout for various these groups. Then GL are not the only groups, there are other types of groups. So people can wonder and work with what is happening with the other types of groups. So this is what is called induction. So building on this GL1 and GL2, Langlands was the one who formulated a theory for GLN and for a general reductive group, not just for GLN. I should also give a small example. Induction is not something which can, directly give you something. For instance, people who are interested in cooking, there is something called as an induction cooker. What is an induction cooker? It is something which comes up with a plate. There is a plate on the top of that cooker, and there are several specifically made pots. So there is no flame. It's not like a gas. You light a gas and then you can boil milk on that, or you can make khichdi, or cook Maggie, or if you are sufficiently advanced cooks, you can do several other hi-fi things. But you will require flame whenever you have a gas or you have a usual stove or sigdi and so on. Flames are there. Induction works without flame. Induction is something which will only pass the heat. So the plate will become hot, and the pot is also specifically designed, which is conductor, a good conductor of it. And the heat then passes on to the things which are there inside the pot. So you don't see the flame, but induction happens and the food is cooked. For that, the plate has to be good and the pot also has to be of correct material. Only then the induction happens. All right. So now we have come to the eighth part. Let me go over the first 7 things again. We had survey, we had observation, we have conjecture, then we had reinterpretation, then analogy, then transfer and induction. Those were the 7 things. Now we come to the 8th part, which is called converse. Or somebody may say that this is conclusion. You could also talk about conclusion, but I will include converse because this is the question, question of the type that whenever some statement holds, say something like A implies B, you can wonder if B implies A. A very simple example is, if there is a rain, if you get up in the morning, come outside and see through your window or from your gallery, if you see the roads are very clean, in Mumbai, in IIT Bombay, the roads are clean. But if you go outside and suddenly in the morning, if you see the roads are clean, it's very natural to wonder whether it rained in the night. This is a very natural thing. Did it rain? Because the roads are really clean. Then you will look at the trees. You will see if there are some raindrops on the trees and so on. What we do know is that whenever it rains, the roads are clean. But you are wondering about the converse. You saw clean roads and you wondered whether it has rained. This is something which may not always be true. Sometimes there may really be some dedicated workers who came and cleaned the road before you even got up. And when you look at the treetops, you see that there are no raindrops, so there is no rain. Then people must have cleaned the road, really. That could happen. This is what is a converse question. Another example, when you have a wire and you pass an electric current through it, then we know from our basic physics that there is a magnetic field that is created. If you have a magnetic field, will it produce an electric current? This question has affirmative answer. Yes. When there is a magnetic field, you get an electric current. So electric current creates magnetic field. Converse also holds that when you have a magnetic field, it will produce an electric current. So some converses are very interesting and there are some natural, beautiful answers. Okay, so these are the 8 ways in which one can ask questions. I will just put them in summary. We have survey, we have observations, conjectures, reinterpretation, then analogy, then transfer of ideas. We had induction and converse. These were the 8 steps. We said that this was our 8-fold way of asking good questions. If you look at only the initials of these 8 steps, what we read is SOCRATIC. This is the Socratic method of asking good questions. You have S for survey, O for observation, C for conjecture, R for reinterpretation, A for analogy, T for transfer, I for induction, and C for converse. So these are the methods. This is one way of asking good questions. I am not claiming that I know everything and this is the only way or so on. There is no other way to ask good questions. No, that's not the case. This is one method. If you apply this method, there is a good possibility that you will come up with good questions. And then you will also know things. For instance, once a critic said to Socrates that, Socrates, you don't know anything. And Socrates calmly replied, I know. So these are some interesting anecdotes from Socrates' life. So what we should do is keep calm and do your research. I hope this is useful to you and thank you for inviting me. Thank you very much.
Thank you, sir. So I would like to request participants that if they have any questions, they can share it on the chat box. Otherwise, you can raise your hands. Shantanu Kadam, sir, you have raised your hand. You can unmute your mic and you can speak.
Kadam sir, please go ahead and ask question. Venkatesh sir, you have a question?
Venkatesh sir, you can unmute yourself and ask the question. Venkatesh sir, are you there? Venkatesh sir?
He has, I think, lowered his hands.
Sir, he put a question in chat box, sir.
There is one question which is asking whether can I cite my paper in next paper? This was Venkatesh's question. So of course, if it is relevant, you can cite your own paper. There is no problem with that. But it has to be relevant. Meaning you should be able to say, you should be able to write 1 or 2 sentences about your paper which are not out of place in the next paper.
So they are saying they don't have any question.
What is exact time to write review paper? There is no exact time. I would suggest that don't go for writing review papers. Meaning if there is a request from some journal saying that, you are an expert on this part and we would like to have a review paper from you, then you may think about it and write review papers, but don't go for writing review papers. Go for writing research papers. Don't write review papers. Never. Not before PhD or after PhD. If you want to write a book. If you think that you have done good research and you know some theory very well and there are no good materials available on that, write a book on that. Don't go for writing review papers. How can one earn or generate revenue from writing the research paper? My goodness, I don't earn revenue from my paper, so I don't know. Maybe, if you write good papers, people will invite you for lectures and many people will learn about you. I think that is something you can earn. You can earn some reputation, you can earn some respect, you can earn this. I don't know how one can generate revenue. Review papers may give research gaps. This is true, but you don't have to write a review paper for that. You have to just, observe. You have to do survey and observe. And this survey and observation can be put inside the research paper. You don't have to write a separate paper for that. This is, I think people are going behind. I'm not saying that Venkatesh sir is doing this, but you people these days have a tendency of going behind writing many papers. They will read something, they will write a review on that thing, and that will be another paper and so on. But many good places like IIT Bombay and so on, they don't look at review papers. They will only look at the research papers. Asha ji has asked whether can I publish one paper? No, you should never republish your papers. Never ever. That is not ethical. Yeah, it's like, you go for work, you are going for some conference or something, and you are using your ticket to get money from both the places, to the conference places and also your place. That is not allowed. Similarly, you should not publish your paper again and again. In fact, it is illegal. Whenever you publish a paper in the journals, there is a binding, there is an agreement that you make with the journal saying that these are original research ideas. You are not using something which is already published. You may use things by quoting. You can say that I am using this result from this paper, which could be my own paper or some other paper. And then you have your own result. But your result itself cannot be coming from something which is there.
Rekha ma'am, you can ask your question. You can unmute yourself. Rekha Patil ma'am. Sir, there is again one question from Venkatesh sir.
Yes, what is the general English test sense I should use during writing abstract and conclusion? So, the thing is that you should, meaning it is considered rude to use the word I when you are writing a paper. You should always say we. We, in the sense that the author who is writing the paper and the reader who is reading the paper, it's about both of them together. This is one nice thing about Sanskrit Bhasha. I don't know how many of you have learned Sanskrit, but there are three what is called vachan in Sanskrit. There is ek vachan, there is bahuvachan, and there is also dvivachan. So here we see dhanyavadaha. This is what I have written in my last slide. This is many, many thanks. So if you know devaha, devau, devaha, prathama is what we say. And whenever there are two, you have Ram Lakshmanau. That is how you say. Okay. So when you write paper, it's about we. It's never about I. And then it should always be in the present tense. We see that this is being done. We ask this question and we try to answer this. This is how the sentences should be in a research paper. We should not say that we have proved or we asked this question and then you write that question. That would not be correct grammatically. We ask, ask, that's it. There is nothing after that. We ask the question and then you write down your question. We try to answer the question in the following situation and then you write the answer in whatever situation you have. That is the correct grammatical sense. Mala male malaha, correct. That is the akaranta strilingi. My Q is present or past tense is in abstract. Abstract also present tense. If there is some work which is done already and you are quoting it, it will be past tense. But the work which is being done in the paper, for that also you will say that we present the work which discusses this question and the answer in this question. Is there any tool for proper grammatical English? Actually, these days there are, even Gmail, if you are writing an email in Gmail, Gmail will suggest to you whether this is, do you want to use this, do you want to use that? So in fact, I tell my students that whenever you are writing any abstract, you should put the abstract in the Gmail as if you are writing an email to me. And then you will see that Google itself will suggest many changes for you and you should apply those changes. That is what I suggest to my students. So these days there are many tools, but that should be a discussion for another paper. Jayashri madam has something. Sir, example, if I submit my paper in good unpaid journal and wait for their acceptance, if the acceptance is late, then can I submit the same research paper to another unpaid journal? But you have to withdraw it from the first one. Only when you withdraw and the other person acknowledges the withdrawal, then you can submit it to another journal. But if you have submitted it to one, you are not allowed to submit to another journal. Venkatesh sir has one more thing. Are you agree that paper review is perception-based opinions? No, the review can also be just, it's not opinion, but it will be some collection of facts also. Meaning somebody can say that, I have studied these things. These are the facts that I have observed. And then when you give opinion, you are giving your own opinion. Then the opinions are always perception based. There is no opinion which is, universal opinion, unless it is coming from often by obtaining some lots of feedbacks and so on. That is not what you have. So one review. Okay, so you mean review in the sense review of the research paper. Correct. Review of the research paper is always perception based. It's about the reviewer. Yeah, true. Where one reviewer accepts, the other one suggests changes. These things happen. One may accept, the other may reject. That can also happen. It is always person based. Whenever there is a human being involved, there is perception and opinion always coming there. True.
Yes, is there any questions?
Why 3 reviewers are there? I don't know why there are 3 reviewers. In fact, to some journals where I send, there are only 2 reviewers, or there is sometimes only 1 person. So 3 is some number which journals reach. Maybe because of this earlier problem that, if one person rejects and the other accepts, you don't know. It's like, India-Afghanistan match. There are 3 matches to decide who is the series winner. So odd number seems to be better. This is why, maybe 3 are there. I don't know. But 2 can also be there. Journals can think that, if both of them accept, it must be a good paper. If one person accepts, another person rejects, the editor can take a call.
Okay. Thank you, sir, for your wonderful expressions regarding art of research. Thank you once again. Now we are towards the arriving at the end of this FDP. Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. I feel honored and privileged to get the opportunity to propose a vote of thanks. I would like to thank Shri S. A. Patil sir, Secretary of the institution. I would like to thank Shri Shivanand Patil sir, Trustee of the institution. I would like to also thank Campus Director Dr. M. A. Chaugule sir, Principal Dr. V. V. Poddar sir. I would also like to thank to convener of this FDP, Professor S. V. Kulkarni sir. I would like to thank event keynote speaker and chairman of IEI, Professor Mohan Deshpande sir, HODs of various departments and faculty members of the AGPIT. I would like to extend my heartfelt gratitude to Dr. Sushil Kumar Pare sir, who gave gracious information about how to crystallize your research idea. I would also like to extend my heartfelt thanks to Dr. Ganesh sir, who expressed about scientific writing for research papers. I would also like to extend my heartfelt gratitude to Dr. M. Nadkatti sir, who explained about the technical writing skills for journal publications. I would like to extend my heartfelt thanks to Dr. Suman Desai sir, who explained about reference management tools. I would like to thanks to Dr. Suraj Boyer sir, who expressed about IPR and patenting, a step towards commercialization. I would also like to extend my heartfelt gratitude to Dr. Shripad Garge sir, who expressed about the art of research. And the last but not least, I extend my heartfelt thanks to all the participants over here. With the permission of dignitaries, I declare that this FDP is over. Thank you once again.